We're moving into exciting new territory here. We're talking about more interesting relationships among variables. We're going to start with contingency tables. As we will see, there are different methods for understanding the relationships among variables depending on their types. We already saw how to compare means or proportions of two groups. This method can be quite useful, but there are lots of situations that are not amenable to this type of analysis. The one we're going to talk about today is the situation where both variables are categorical and at least one has more than two values. If both variables are categorical and both have only two values, a simple difference of proportions would work. In this more complicated case, where categorical variables have more than two values, we need different tools. Here are a few examples of the types of relationships that we could explore. What's the relationship between social class and vote choice? What's the relationship between religiosity and partisanship? And what's the relationship between regime type and conflict? All of these are questions that would be hard to answer with the technology that we've developed so far. Contingency tables are the building blocks of understanding relationships among categorical variables, both ordinal and nominal. We sometimes refer to contingency tables as cross-tabulations or crosstabs. There are a couple of different ways that you can make contingency tables, but there are some clear guidelines for how they should be made to make analysis most straightforward. The dependent variable, the variable you're trying to explain, should be in the rows of the table. That means its value should be arrayed down the left-hand side. The independent variable, the variable you think helps explain the dependent variable, should be in the columns of the table. That means its value should be arrayed across the top of the table. Each cell should contain a frequency and a column percentage, the frequency divided by the total number of observations in that column of the table. You should compare column percentages within the row, looking for the biggest value or the biggest differences between values. First, we'll look at a template, and then we'll look at an example. Here's a hypothetical table. Note that the table is organized the way we discussed in the previous slide. Let's look at the top left cell. Here the frequency is F11 and the column percentage is F11 divided by the sum of all of the frequencies in the column, F11, F12, and F13. Let's look at a real data example from the book. This is an example from the book where we consider the relationship between the independent variable gender and the dependent variable response to a pizza commercial on TV. Note that the values in the percent column are column percentages. 1.6 is just equal to 10 over 620 times 100 to make it a percent. 9.7 is just 60 over 620 times 100 to make the proportion into a percent. And 79 is just 490 over 620 times 100 again to make it into a percentage. Next, we compare those column percentages within each row. This provides several insights. Looking at the last row, women are much more likely to have no reaction than men. Men are a lot more likely than women to order pizza, and a little more likely than women to get food from the refrigerator. Women are quite a bit more likely than men to just change the channel. The question that is really important that we can't answer from these numbers is the following. Are these differences sufficiently big for us to think that something interesting is going on in the population? We turn to this next. The chi-square test for independence allows us to make inferences about whether the contingency table we're looking at is likely identifying real differences in the population or just picking up random noise. We calculate the chi-squared statistic for each cell, which is simply the squared difference between the observed and expected frequencies divided by the expected frequency. The observed frequency is just the count in each cell. The expected frequency is what we would expect the frequency to be if the two variables were, in fact, perfectly independent. We can calculate the expected frequency by multiplying the column marginal, or total value, by the row marginal, or total value, and then dividing that product by the total number of observations in the entire table. Let's work through an example. I've replicated the pizza commercial contingency table here without the column percentages because we're going to calculate and fill in some expected values. If we start with the expected frequency of ordering for females, it's the product of the column marginal value, 550, and the row marginal value, 40, divided by the total number of observations in the table, which is 930. This gives us a value of 23.66. We could do the same thing for men, taking the product of 380 and 40 and dividing that product by 930, which gives us 16.34. Let's fill in the rest of them. You're welcome to pause here and calculate a couple of the others by hand if you like to make sure that you understand how the formula works. Next, we can calculate the chi-squared statistic for each cell. The first two columns in the table are the observed and expected frequencies. The third column takes the difference between the first and second, and the fourth squares the difference that we calculated in the third column. The fifth and final column divides the fourth, the squared differences between observed and expected frequencies, by the expected frequency in column 2. Summing up all the entries in the fifth column gives us the chi-squared statistic of 22.22. Because you're not intimately familiar with the chi-squared distribution, you likely don't have a frame of reference for whether this is a big or small number. To figure this out, we need to know a few other things first. Under the null hypothesis, the chi-squared statistic follows a chi-squared distribution with degrees of freedom that are equal to the number of columns minus 1 times the number of rows minus 1. In this case, the chi-squared distribution has 3 degrees of freedom. It's also worth noting that this test only works if each cell has an expected count of at least 5. There are alternatives we'll talk about in class if this isn't the case. Here's what a chi-squared distribution with 3 degrees of freedom looks like. What we'll want to know is what the area under the curve to the right of our chi-squared statistic looks like. It's easy to see here that very little of the area is to the right of our chi-squared value. In fact, the actual percentage to the right of our chi-squared statistic is 0.006%. This would suggest that our data are not consistent with the null hypothesis. Speaking of the null hypothesis, the null for this test is that the two variables that define the contingency table are independent in the population. The alternative hypothesis is that the two variables are related, that is, not independent, in the population. Notice that the hypothesis has no direction to it and, unlike some of the other hypotheses we looked at, cannot have a direction to it. Rejecting the null indicates that there is likely a relationship in the population, but we still have to figure out what it looks like. In the example above, we noted that men were on average more likely to get food and women more likely to change the channel or ignore the commercial. We'll talk about some other ways of presenting this information when we get together in